What if the proof that we're not alone didn't arrive in the form of a message, a spacecraft, or a shimmering alien city, but instead in a handful of dust scraped from a crater on Mars? In early 2025, the headlines exploded with one haunting question: did NASA just find life on Mars? The idea sounds sensational, almost overplayed. Yet this time, something feels different. Beneath the usual media noise lies a discovery so subtle yet so scientifically stubborn that even NASA's own researchers admit they can't explain it away. At the heart of the story is the Perseverance rover, a six-wheeled geologist that's been crawling across the Jezero crater since 2021, a place long suspected to have once been a lake. This ancient basin, once fed by a Martian river delta, holds sediments that could preserve traces of life if it ever existed there. For years, Perseverance drilled, scanned, and sampled, searching for the faintest chemical fingerprints of biology. But in late 2023, a particular rock nicknamed Yori Falls changed everything. Its surface was mottled with dark, almost leopard-like spots. Inside those tiny markings, the rover's instruments detected something astonishing: complex organic molecules. Not random chemicals, but compounds that on Earth are often linked to living processes. Suddenly, scientists were forced to ask the question out loud again. Are these molecules remnants of ancient microbial life, or could they have formed through chemistry alone? On paper, there's a world of difference between organic matter and life. Organic molecules are the building blocks, carbon-based compounds that can appear through geological reactions, as well as biological ones. But when these molecules are found together with certain mineral structures, as Perseverance observed, the pattern becomes harder to dismiss as mere coincidence. Adding to the mystery, the rover detected strange enrichments of iron and phosphates, two ingredients that on Earth often accompany microbial metabolism. It was as if the Martian soil was whispering an unfinished sentence: something once lived here. Of course, NASA scientists have seen this movie before. From the Viking landers of the 1970s to the meteorite AL8 4001 discovered in Antarctica in 1984, every generation of Mars research has carried its own false dawn. Each time an anomaly was found, a chemical spike, a fossil-like shape, and each time later tests unraveled the excitement, revealing contamination, misinterpretation, or purely geological origins. But this time, researchers led by geologist Joel Juritz took a different approach. Instead of looking for proof of life, they tried to disprove it. Working under a null hypothesis, their goal was to exhaust every non-biological explanation first. Yet after months of analysis, one uncomfortable fact remained: there was no purely geological process that could fully account for the minerals and chemical distributions Perseverance recorded. The rocks contained vivianite and greigite minerals that on Earth commonly form through microbial activity in ancient lake beds, when tiny organisms recycle iron and sulfur as part of their metabolism. In scientific terms, this is called redox cycling, a process that leaves behind distinct mineral fingerprints. The same fingerprints now appear on Mars. To some researchers, that alone borders on the extraordinary. Because if those minerals truly formed the same way as they do on Earth, the simplest explanation might also be the boldest one: that Mars was once alive. And as NASA's own Michael Tice put it in one striking quote, "If there had been life, it would be an easy explanation for what we found. But if there hadn't, it becomes incredibly difficult to explain." The line between evidence and proof has never felt thinner. To understand why this finding is shaking the scientific community, we need to look at the chemistry behind it. On Earth, vivianite and greigite, the two minerals Perseverance found, are born in calm, oxygen-poor lakes where microbes thrive by feeding on iron and sulfur. These microorganisms alter the surrounding sediments, leaving subtle patterns in the minerals they touch. It's like a biological signature written in stone. The mystery is that such transformations don't easily happen without life. Chemical reactions alone can form these minerals, yes, but they require extreme environments, temperatures above 150 degrees Celsius, or conditions so acidic they would dissolve most rock. The Jezero crater shows no sign of either. In fact, Perseverance's instruments indicate that the area was mild wet and surprisingly stable conditions friendly to life, but not to those violent chemical reactions. This contradiction is what makes the Mars biosignature debate so gripping. If there were no microbes, something else had to drive these transformations, yet no purely physical process fits the data. Scientists have spent months running simulations, comparing spectra, and reviewing every possible non-biological pathway. Still, none of them explain the fine layering, the ratio of iron oxidation, or the exact distribution of phosphates detected by the rover. It's as if the rocks are following a rulebook that only life seems to know. This isn't the first time humanity has stared into such uncertainty. Decades ago, the Viking missions performed an experiment that looked almost too successful. They mixed Martian soil with a nutrient solution tagged with radioactive carbon on Earth. Microbes would metabolize the nutrients and release gas. The Viking sensors detected that gas, suggesting something was alive. But follow-up experiments couldn't replicate it, and later scientists discovered perchlorates in the Martian soil chemicals that could mimic biological reactions when heated. The dream of life on Mars collapsed into skepticism. Then came the Antarctic meteorite in 1984, AL8 4001. When scientists saw microscopic cell-like structures inside, President Bill Clinton himself made a public statement about the possibility of extraterrestrial life. But later analysis revealed the structures were too small, more like viruses than bacteria, and could have formed without biology. Each time hope flared and then cooled. That's why this new discovery has scientists walking a tightrope between wonder and restraint. The Perseverance team avoids the word life. Instead, they say potential biosignature, a cautious term that means possibly biological, but not proven. The difference matters. It's the line that separates revolutionary science from wishful thinking. Yet even this restraint can't hide the excitement simmering under the surface. The Mars data refuses to behave like mere chemistry. The minerals align with microbial fingerprints, the organics appear where water once flowed, and the surrounding sediments tell a story of calm lakes that could have lasted for millions of years. It's not proof, but it's a whisper that won't fade. The deeper scientists dig into Perseverance's data, the more the evidence seems to defy a simple geological narrative. Under magnification, the mineral grains reveal patterns that mirror the same redox cycling processes seen in Earth's ancient lake sediments, those delicate exchanges of electrons between iron, sulfur, and carbon, that on our planet are almost always mediated by life. What fascinates geochemists is how neatly these patterns match microbial models and how inconsistent they are with sterile chemistry. If this discovery had come from any other planet, it might already be celebrated as proof of past life. But because it's Mars, our long-obsessed neighbor haunted by false alarms, scientists are cautious, even skeptical of their own enthusiasm. The investigative team led by Joel Juritz knows this history well. That's why they worked under a deliberately conservative framework, asking one question: can we explain this without life? Their conclusion so far, not convincingly. Yet that statement opens a floodgate of possibilities. If these mineral formations are indeed biogenic, formed by living organisms, it would mean Mars once hosted ecosystems at least as chemically sophisticated as early Earth. That single revelation would rewrite the history of the solar system, suggesting that life might not be an Earth-exclusive accident, but a cosmic pattern. It would also force us to revisit the idea of panspermia, the hypothesis that life can travel between planets, possibly hitching rides on meteorites. If microbes once thrived in Jezero crater fragments, blasted off by ancient impacts, could have seeded other worlds, perhaps even ours. In that sense, humanity might carry Martian ancestry without knowing it. Still, the data leaves room for doubt. NASA's Katie Stack Morgan warns against jumping to conclusions, reminding the public that abiotic explanations, non-biological ones, can never be ruled out completely until we study the rocks here on Earth. The challenge is that Perseverance can only analyze so much. Its onboard instruments, while advanced, are limited compared to terrestrial laboratories. That's why NASA and the European Space Agency planned the Mars Sample Return Mission, a multi-billion-dollar effort to bring those precious rocks home. Originally slated for 2032, the mission now hangs in limbo due to budget crises. Engineers and scientists are frustrated. Every year of delay means another year the world waits for answers. Meanwhile, every new analysis from Perseverance adds tension to the mystery. Some see this as evidence of the great filter, the idea that life might be common, but complex life is rare or self-destructive. If Mars once had microbes that later vanished, could that be the universe's warning? The red planet might be a graveyard of its own biology, a silent witness to how fragile life can be when a planet's climate collapses. Others see optimism if Mars could harbor life. Once then, life might bloom anywhere. Water flows beneath Europa's icy crust, in the methane lakes of Titan, or even in the hazy clouds of Venus. The question isn't just, did Mars live, but how often does life happen? Are we the exception, or just one chapter in a vast biological continuum that the cosmos keeps rewriting? What Perseverance uncovered isn't merely about rocks or molecules, it's about possibility, the kind that forces us to confront what we thought we knew about existence itself. Because if microbial life emerged twice independently in one small solar system, then statistically the universe is alive. The numbers would demand it. And yet, for all the excitement, we remain suspended between revelation and restraint. The truth about Mars will not come from one sample, one image, or one lucky data point. It will come from the patient process of elimination that defines real science. For now, Perseverance continues its slow crawl across Jezero Crater, collecting cores that could one day rewrite cosmic history. Each sample tube it seals is a time capsule preserving an ancient Martian environment, frozen in dust and stone. Inside may lie the fingerprints of life, or the flawless imitation of it. The suspense feels unbearable because humanity has stood at this edge before peering over the cliff of discovery, only to be pulled back by uncertainty. But this time, something feels different. The data doesn't just hint, it insists. The ratios of iron, sulfur, and carbon defy randomness. The presence of phosphates, the subtle isotopic variations, the distribution of organics all point toward a world that once breathed chemistry with purpose. If it isn't life, it's something so close it forces us to redefine what life even means. Imagine for a moment what confirmation would bring. A Martian biosignature verified beyond doubt would mean we share this solar system with another birthplace of biology. It would shatter the illusion of solitude that has shaped human thought for millennia. Religion, philosophy, and science alike would need to confront the fact that life is not unique, not fragile, not rare, but inevitable. Even a fossilized microbe on Mars would echo through every telescope and classroom on Earth, whispering the same message: we were never alone. But reality is colder. The Mars Sample Return Program, the mission that could finally prove or disprove this discovery, is stalled. Political debates, funding issues, and engineering delays have pushed the return date far beyond its original 2032 goal. Each postponed year feels like a metaphor for human hesitation, as if our civilization isn't ready to meet its cosmic twin. And yet, in those delays lies a strange beauty. The mystery persists untouched, daring us to keep asking questions. Scientists are right to be cautious. Every false positive from the past, every misread signal and misinterpreted shadow has made the search stronger, more precise, more honest. But one can't help feeling that this time the evidence is whispering louder than ever. The minerals speak a language older than humanity, and somewhere in their crystalline code might lie a story about the first breath ever taken on Mars. Whether that breath came from biology or blind chemistry remains uncertain. But perhaps the greater truth is this: the search itself defines us. Because in chasing life beyond Earth, we are really searching for the limits of our own. So the question remains, when those Martian samples finally arrive, will they prove that life began twice, or that it never truly ends?